It's my great pleasure to have today's presentation of Djahid Rabehi. He's from INSA Lyon currently, and before that he received his Master of Science degree in automatic control from the Université de Lille in France. And this was in 2017, and afterwards he joined the working group of Nassim Ramdani at the Université d'Orléans, where he received his PhD degree in November 2019, if I'm not wrong. And we're looking now forward to your presentation on an event-triggered interval observer design for continuous time linear system, which is based on an L1 gain approach. The floor is now yours.
Okay. Thank you for the introduction and hi everyone. Today I will give a talk about event-triggered interval observer design for continuous time linear systems with the finite L1 gain approach. This work is done during my last year of PhD with collaboration under the direction of Professor Nassim Ramdani and Nassim Meslan. The considered system here is cyberphysical systems. Cyberphysical systems are composed with physical systems, which is naturally continuous model, and the cyber component composed with the computers and the networks, which is naturally discrete models. Here, the presence of network has a lot of advantages, but the networks with the finite bandwidth can introduce some limitations, such as the sampling may it's affected and will be irregular or even aperiodic. In control theory point of view, this problem can be relaxed with the considering sampling or irregular sampling or aperiodic sampling, or even to control this sampling based on some events to relax or to minimize the load of on network. Here in this project, we will focus on this work. We will focus on the event-based sampling or event-based measurement for interval observers. Here, the interval observer. I will give a rapid introduction to interval observers, and I will pass through the details of the project. Interval observers mainly are classical observers that give an upper and lower bounds of the admissible set of the state or the variable states. They have some applications like estimation of biological system or fault detection and diagnosis, and also for control of uncertain systems. Some works related to cyberphysical systems or some systems related to cyberphysical systems are switched systems. It can model a sampled or sampled system or impulsive system and sampled system. All these systems can model a cyberphysical system with these works in the literature. Here, the objective is to design interval observers with the event-triggered sampling for continuous time system. The idea is to estimate the continuous state based on measurement that are based on the quality of estimation or also the stability of estimation. And second one is the QDesign, the gain of interval observer and the event-triggered mechanism or event-triggered condition of sampling. Now I will give, after the problem statement, I will give some background on positive dynamics and hybrid systems. Then I will talk about the finite L1 GAN event-triggered interval observers and a structure in general, and how to design the event-triggered conditions with the interval observer GAN. And I will conclude with some conclusion and perspective. So the system considered here is the linear continuous time system with unknown but bounded perturbation or input, and the measurement is considered discrete. And we consider here that the system is measured or estimated over network. So the measurement is discrete and also noised. And then with the working assumption that these perturbations are known, but with the known bounds. Mainly, the interval observer is two estimators that estimate the upper bound, like Lemberger, like classical observer that estimate upper bound and lower bound of the admissible state of the system. This kind of observers should satisfy two conditions: the non-negativity of the errors. This bound enclose all the time the state of the system, and the error between these two bounds should be stable. And in this and for the stability of this system, we will use hybrid system framework. First, I will start with the positive systems. System is monotone if the solution respects some order relation from the initial condition, like given by this equation or this implication, I mean. For linear system, continuous time system is positive or cooperative if its state matrix is Metzler, mainly if has off diagonal elements positive. And for discrete time system, system is non-negative if the state matrix is non-negative. All elements are non-negative. And we call them cooperative system for continuous time system and non-negative system for discrete time linear system. If these systems don't respect this condition of non-negativity or cooperativity, there is some approaches to make them cooperative, like change of coordinates and by diagonalization, or make the system under the Jordan form by using time variant or time invariant transformations. Other approaches are based on, sorry, how to close this? Okay. Some other approach called the internal non-negativity is to, always for linear system, is to decompose the state matrix into two cooperative matrix. non-negative and Mitzler, or two non-negative matrices for discrete time system, like the example 1 and example 2 for discrete and continuous time system. Now I will talk about the hybrid system framework used here. In general, this system are modeled with a flow map exponent called F. Whenever the state is in the continuous set, and the jump map whenever the state is in discrete set. A classical example is the bouncing ball modeled by the flow is the continuous dynamics, where we the x1 is the position and x2 is the velocity. And here the system, the position is not discontinuous, but the velocity is discontinuous in the jump map G of x by a jump with the minus lambda. Lambda is just the bouncing coefficient. And the discrete set is whenever the position is 0. So when the ball collapsed in the solid, so the state is in the discrete set. So it trigger the jump. Here we use generalization of the stability of hybrid system called the ESS stability or LP gain stability. The stability it's mainly it's combined the ESS or the LP gain stability for continuous time system with the discrete time system. With this definition, so the Y here is in our approach is the width of estimate, and the D is the perturbation, and again between these two between the input and this input and the output is the gain gamma p, which called the finite gain LP. If it's limited, so the system is finite gain LP stable. The detailed definition is given by Nesik et al. And his co-authors. So mainly the condition is we should find the finite gain storage function or Lyapunov function that satisfy the condition to be is the ESS or the LP stability for continuous time system, and the 2C is for the discrete time system. So if these conditions are satisfied, so the system is a finite gain LP stable. And the upper bound of this gain is given by this estimation. Now let's introduce the structure of our observer. Here the observer is mainly have two behaviors. It estimates the state of the system between two measurement time by prediction based on the model. So here we for the first open loop estimation, AO equation AO is based on only the knowledge of the system and the input and the bounds of the perturbations, without knowledge of the output. Then it predicts until the presence or until overcome some threshold, and then the algorithm or the event triggered condition will trigger a measurement to correct this estimation based on this the second part of the observer. So it's like Kalman filter, but with deterministic properties. So we estimate an interval, and then we correct if this interval pass certain or some threshold. We request the measurement to correct this estimation using the output. The error dynamics, I will go in some details here, but it's not deep. So the error dynamics, based on the two structures that I have presented right now, are given by these two, the flow dynamics of the estimation error and the jump dynamics. And this we have construct this observer in a way that the M of A is AM is a Mitzler matrix and AN is a non-negative matrix. So all this matrix is Mitzler. And the same thing for the second, for the jump matrix. So the correction, the jump matrix is I plus LC. The L is the observer gain. The plus means that the is the positive part of this matrix, and the minus is the negative part, but in absolute value. So this matrix is non-negative. Here, the jump, the state matrix of the flow and the jump are non-negative or are cooperative. And the second part about perturbation is non-negative based on these chosen structures. So here, structurally, by construction, the system, the estimation error is non-negative, is always non-negative. The problem here with the event triggered mechanism is that the continuous set and or the flow set and the jump set are based on the XI. XI is by definition the error, the upper bound error and the lower bound error. And these errors are by definition based on the state. So when we have some information about states, we don't need to do the trigger to estimate the state. We can use directly this condition and estimate continuously the state. If you have access, I mean, if you have access to this condition continuously. To relax this condition, we have used the some properties of interval or norm one and bound or interval observers or negativity. We know that the the interval of between the upper bound and lower bound, it contains always the state. So this the sum of these errors equal to the interval omega here, or the W, sorry, width, equal the width here. So we can use only the estimate to the upper and lower estimate to in our event trigger mechanism. And the other properties is that the norm of width of the width and the norm of this estimation error are equal, the norm one. And it's the same with the width of perturbation. So we can use only the known bounds to trigger or to satisfy these or to shake these two inequalities, to switch between the continuous set and the jump set. And by these two equalities, we can say that the L1 gain of the operator between the Xi, the estimation error, or the augmented estimation error, from Psi to Xi is equal to is the same norm between the delta and the W. So the mechanism, or the event-triggered mechanism, become between the delta of or the width of perturbation and the width of estimate, without knowing the state or the real state or the real perturbation. We just use the upper and lower bounds to control or to control the events when we request the measurement. To design this mechanism, we first fix or we fix the interval observer gain L is fixed, and we shake these inequalities to estimate the mechanism is based on beta. So beta here is the coefficient for the mechanism, and this zeta is just an S procedure. If I return here, we have a dynamic here and we have condition. So we have used the S procedure to introduce these inequalities into these dynamics to get some inequalities based on the Lyapunov functions. So the proof of this theorem is based on linear compositive Lyapunov function. We use this analysis with this function, this function, and we add the event-triggered mechanism by in the inequalities or Lyapunov inequalities by the mean of S procedure, and we should satisfy these inequalities to find we have to solve these inequalities to find the event-triggered mechanism based on beta and zeta and these parameters. If these conditions are satisfied, so our observer is a finite L1 gain interval observer, and the L1 gain between the width of perturbation and the width of estimate is upper bound by this value or our approximation. Here, enter there is some limitation in about the existence of minimum interval event time. If we start the estimate with the very big value or very big interval, so we have to trigger continuously to get into under the threshold, and these it's not realizable in over network or over a limited network. Limits the bandwidth network. So we have extend this approach using the work of Girard about dynamic event-triggered mechanism. So here we have add some auxiliary variables, which is based on the difference between based on our mechanism. The inequality is our mechanism. So we have to start just this auxiliary variable with the big value, and then it will converge exponentially to this bound, to beta bound. And the conditions for this the mechanism are given by inequalities 9. And here we use Lyapunov function, or Lyapunov function is like the last function plus the new auxiliary variable, and this variable is by definition non-negative, so we can use it in the Lyapunov function. And by analyzing these ratio between the width and its bound or its threshold, we can find that there exists an enter-event time. So there is a minimum time between two events. Now I will pass to the QDesign, how to design the observer GAN and the event-triggered mechanism parameters. Here in the event-triggered mechanism, we have beta and theta. Beta and there is another coefficient. Yeah, beta and alpha, the dynamic parameter for the auxiliary variable, or the constant of the dynamics of the auxiliary variable. Now to QDesign these two or all parameters, we mention here that in blue the parameters to be designed. Gamma of L is the matrix dependent of the the observer interval observer GAN matrix. Sorry, here we will use instead of design directly the L matrix, we will look for some realization for the positive and the negative parts by matrix. We call it G, for example. We call G E plus LC, and here we have for all GP and GN non-negative, we have some positive delta such that the G plus delta minus the G minus plus delta equal always equal G. Here the G plus is just this matrix with the plus or the positive elements of this matrix, and the G minus is this matrix or the negative elements of this matrix with absolute value. There is an example to show this that demonstrate this. For this matrix, which is not non-negative, we can find two realization, positive realization, and then we subtract this delta matrix to find our positive elements and non-negative elements. So we use, instead to design the L matrix, we will design the GP and GN, and with some constraints. With these constraints mainly, G equal I identity matrix plus LC. Based on the definition or the method that I have presented, instead of looking for gamma of L, we will look gamma of GP and GN. So we have to find some realization GP and GN for this matrix. And then by definition, we have already that delta is positive. So if the gamma, if the jump matrix based on this gamma GPGN is stable, this jump dynamics is also stable. By this proposition, we can find more details in the published article. So based on this internal positive realization, we can design directly the GP. We can design the GAN, the L matrix based on GP and GN with another intermediate variable with the same technique, RP and Rn. And lambda here is the Lyapunov vector for a positive copositive Lyapunov function. 2 zeta are just the variable or S procedure variable, and the gamma are the elements of the L1 GAN. And here the alpha beta are the coefficients or the parameters of our event trigger mechanism. So we designed our observer GAN L and alpha and beta using these inequalities with the other ones that we have presented in inequality 9.1 and 9.a and 9c. Sorry. And this the found observer is a finite L1 GAN interval observer for the mentioned system that guarantee the existence of positive minimum the existence of minimum interval minimum inter-event time. Now I will pass to the application. The application is just by simulation for a system or double spring mass damper system with the LTE dynamics. Given is a continuous time system. We solve the inequalities using fmin-con is classical solver. For here we fix the theta is a parameter of event triggered is the only hyperparameter that we fix, and then we design our observer GAN and the parameters of the event triggered mechanism using the inequality that I have presented just right now. And the obtained result shows that here the two positions, position for the mass 1 and position for mass 2, and the velocities. It shows that we can estimate continuously the state, not continuously, but in continuous time, but in the event there is some jumps due to the correction based on the measurement, and the estimate converge to some finite error with the L1 GAN stability. In this figure, we show the threshold in the black line, and the blue is the width of estimate. So we can see that at each when the width equal the threshold, we request the measurement to contract this estimate, and we can show that we have an inter-event and minimum inter-event time estimated to this two mean. So I will conclude with I will sum up with some conclusion. In this talk, I have presented the design of event-triggered or design of event-triggered observer that can reduce the occupation of the network in cyber-physical system estimation, and a new design QDesign technique for interval observer gain and dynamic event-triggered mechanism for LT systems. As perspective, we can extend this approach to nonlinear system. For example, systems that can be over-approximated by linear system, and also design of output or event-triggered output feedback stabilization law using this interval observer. Thank you.
Okay, many thanks for a very interesting and inspiring presentation. And now we definitely have enough time to ask some questions. Luc, do you want to start?
Yes. I see that Carlos has a question also. Okay, I start. You can hear me? Yes.
Yeah.
Okay. So my first question is, it was during the implementation, when you implement your observer in the machine. So you should integrate a differential equation which is linear. It seems yes, it is linear.
Yeah.
And here you assume that you are able to do it in a guaranteed way, or in your implementation you integrate the linear differential equation in a guaranteed way, or you integrate numerically as we do classically?
For the integration, I have used Rensch-Kutafor approach.
Yes,
but I don't understand what do you mean. But for the integration, I integrate to two bounds separately, like a linear system.
Yeah, yes, I understand. But if you take one of these bounds, you will use a Runge-Kutta method. But use your Runge-Kutta method. If, for instance, you want to estimate the upper bound, your Runge-Kutta method will give you an approximation of. But how?
Yeah, of course.
But do you guarantee that what you obtain by the Runge-Kutta method is another approximation of this upper bound? You understand what I mean? Or you assume that the Runge-Kutta method is perfect?
Yeah, I assume that it's perfect.
Okay.
Yeah.
Okay, so you do not plan to do everything guaranteed. You could also.
I don't understand what is the problem with the Runge-Kutta in this context.
The approximation of the Runge-Kutta will not compute the exact bound. It will compute an estimation of the upper bound you want to get.
Okay,
but you don't
understand.
know if this approximation is an under or an upper evaluation.
Okay, I understand.
But maybe in your reasoning, you just assume that your Runge-Kutta method is perfect.
Yeah, we assume that the precision of Runge-Kutta is better than what we look for. So it's for me, it's precise.
Okay, so you neglect the error obtained by the Runge-Kutta method.
Yeah, exactly.
Okay, that was my question. Okay, thank you very much.
Thank you so much.
Thank you.
Thank you.
Okay, then I think let's hand over the microphone to Carlos.
Yes, hello. Hi, everyone. Hi, I really like your presentation. I think it's quite nice, and I already read your article because basically I'm working with Professor Nassim. So I know a little bit about your article, and something in particular that I found very interesting and that I really do not like is about why do you assume that the bounds of the uncertainties and the bounds of the measurement noise are the same. In general, they aren't, and this is, I mean, when you check omega and delta, they have the same bound. You put it like this is a requirement that you need. So my question is more about why. In what kind of context can you use it, or can you have exactly the same uncertainty? Because what I'm assuming is that the sensor in general is quite precise, and the uncertainties are larger than the uncertainties in the sensor. So, sorry, yes, from the tolerance in the sensor. So in general, you have a larger uncertainties process and a really small noise in the perturbation in the sensor. So they are different. So why do you have to assume that they are the same? And if I have a case where they are not the same, what can I do? What can you do?
Yeah, yeah, I understand the question. Actually, here you mean, sorry if I reduce this one. Okay. You mean this equation, I think. For example, here, your question is about this, why we have D here and here in the same time. Why
yeah,
we consider
exactly. Exactly.
Actually, we can, D here can be a vector of noise and perturbation, and then the E, the matrix E and the matrix F be a selection matrix. Here,
okay, no. My question is, yes, it's more about not that they are exactly the same later. It's about why they have to get exactly the same bound. I mean, dt is bounded, so that it shouldn't be the same that in the measurement output. I mean, because in this case, y of tk is an output. It's something that you are measuring every time to time. So this it shouldn't be. Okay, yeah.
The bound is not scalar. I understand you, but the bound here is not scalar. In the assumption, sorry, the assumption somewhere here, the bounds are not scalar, so it can be a vector of bounds of noise and bounds of perturbations. So it's not scalar. And delta here is maybe the delta, the norm one of delta make together all these together, but in D here is vector. It can have or can.
No. Let me see. I can express myself better. In this case, you have one equation, one continuous equation. In this equation, is x of t prime ax plus bu plus some noise. Right? This noise corresponds in general to a non-linearity that you don't know it, to an unknown input, to any uncertainty that you don't know it. This is EDT. Okay. Now you have the output. The output is y of tk, and the output is gonna be perturbed by some problem with the sensors. I mean, because my sensor is not so accurate. So this T, this FD, it shouldn't be the same D than the previous one. They are completely different uncertainties, and the bounds of this D and the bound of the uncertainties that you have in the process are different. I don't know if you got to. So
I don't understand why they are. I don't understand why this generalization doesn't work with your assumptions. If I use a vector D with D here is not a perturbation but a vector of all the uncertainties, and the F is just a selection.
Maybe let me step in. Maybe I understood Carlos' question, because X is a vector of length n. You say also D is a vector of length n. If you have, for example, different disturbances in each component of the vector X dot, you have identical length of the vector D and identical length of the vector X. Maybe in order to resolve your problem, the vector D should be longer than X even.
Yeah, I understand. Yeah, it's different. Maybe more, maybe less, but it's different.
Yes, and if you have,
it's different.
Yes, and if you have more degrees of freedom, I think then I think your explanation works. For example, if your vector X is a 3-component vector and D, for example, is a 5-component vector, you have 2 measurements, 3 states, and the first 3 entries of D will be state disturbances, and the last 2 ones will be measurement disturbances.
Yes.
I think this is a confusion concerning just the length of the vectors.
Yeah, maybe the length. Yeah, but I have worked on this in general. I didn't precise which component is noise and.
Okay. Yes, I think. Yes, I think maybe that's the question. I'm not completely sure about the answer, because my problem is about the bounds. It's about this D bar, this up bar that you have in each entrance. I mean, yes, you can measure all the state, or you can measure only one state. It doesn't matter. The problem is that one of the assumptions that you have later is that the bound of the norm 1 of omega is have to be the same than the norm 1 of D1 of D. So it means that you are assuming that the maximum bound uncertainty that you can receive in the process is the same that the maximum bound that you can receive in the output. So it's something like I have an uncertainties problem in the state X, and every state is going to be perturbed, is going to be under some uncertainties until 0.5, but the sensor is also 0.5, the uncertainties that can receive. I mean, it's about the maximum bound. So yes,
okay.
it's why do they have to be the same? And because in general they aren't.
Yeah, I understand the problem. Yeah, you have reason.
Okay, and I have another question, and this is about your results in the last section, where you have a really nice curve and you see how they are triggering.
An example?
Yes, in example. This one, yes. At the end, I don't know, between 3 and 5, for example, or even before, you can notice that all the activation looks like they are periodic. Did you check it? And this is periodic from this time? I mean, with your methods, you are assuming, or as a consequence, the final event trigger estimation isn't periodic. I mean, of course, I cannot judge if this is periodic or not, but look like every time that they occur is after around 2, I think, is periodic. Is this true, or is just how they look?
I don't have proof that it's periodic, but in this simulation is periodic because we use the same prediction model, so it increment like this, and the threshold after that I think is constant because the eta variable will converge to 0 because exponentially. And the second term will stay constant. So the threshold stay constant. We in this after I think after 4 or something like that, we will work like omega compared directly with beta delta. So the omega has the same behavior, same divergence behavior. And then when this norm of W equal to beta delta, which is constant, so it correct the measure the estimate.
Yeah, the estimation occur is periodic then.
So
at the end, yes.
I think it's periodic.
Yes.
After the convergence, after the annulation of this eta.
Okay, got it. Thank you.
Thank you so much.
Nice work here.
Okay, do we have any further questions? Maybe let me ask a question. Could you go back to the slide 29?
29. Okay.
Is your system model. You assumed in this case that the structure of your system output is constant, that means you're just measuring the first and third state variable here, or something proportional to the first and third state variable all the time. As soon as you detect that your uncertainty passes some threshold. Did you investigate also a strategy that allows you to select the number of the output which you want to or need to measure in order to obtain your contractance property? Because this could even further reduce the complexity in a, let's say, a high-dimensional system model. You may have, let's say, a high-dimensional electric power distribution network, for example. You have the full system output matrix C measuring a lot of state variables or something proportional to a lot of state variables. You already managed to reduce the complexity by reducing the sample or reducing the sampling frequency just by your selection strategy, by your event trigger strategy. And maybe you could even further reduce it by just measuring a subset of the available outputs in a somehow intelligent way that still preserves observability of the system. Did you look into this?
No, actually, I didn't investigate this. The choice of output matrix. In the beginning, I had just one order system, or how to just sample system, sample spring mass damper with the measurement of position. So I have developed for the double spring mass damper with the measurement of 2 positions to be more realistic. I didn't manipulate the choice of other or
yes, because if you look at these equations, I think, if I'm not totally wrong, the system remains fully observable if you just measure one of the positions. Because then the first line of the observability matrix is something 2, 0, 0, 0. The second line will be 0, 2, 0, 0. The third line will be twice the second row of the matrix A. And the fourth line would be a scalar product or something depending on a scalar product of the second and fourth line of your system matrix A. And I think this remains fully observable in the case that you still only measure either the first or second mass position.
I didn't.
As long as the K3 and C3 are not equal to 0. I think this will remain observable. And then you could do something, then you could restrict, let's say, reduce the complexity of measurements just by saying, okay, at the moment it makes sense to just measure the first mass position or only the second one, or in some cases, both of them. This could be maybe something interesting as an outlook on future research, and yes, maybe we could even collaborate on this. Because I recently talked with my PhD student, Marit, who is also here in the audience. We recently talked about a similar problem that could really be interesting as some, let's say, an extension of such an event-triggered observer design.
Yeah. Okay.
Yes, if there's no one else in the audience with a question, I have a second one. Did you also check which conditions would change in the case that your system dynamics is right away described with a discrete time system model?
Sorry?
If your system dynamics at the moment are currently described by a continuous time model, what would be changing if your system dynamics are already discrete time?
It's problem. I have tried to find something about that, but I didn't how to say, I didn't successfully develop the theory behind.
Yes, because I could imagine that there are scenarios where you just have to cross your barrier, this barrier omega, at some point of time, because there doesn't exist any solution of this event-triggered request for measurements without surpassing the threshold.
Yeah, I didn't think deeply in this problem, but I have tried on it, but it was hard.
Okay, let's say it's just an outlook on future research.
Yeah, maybe.
Okay, we have a question from Marek. Marek, please go ahead.
Yes, I have some problem with slide number 18. Can we go? Oh,
This one?
no.
No,
Sorry,
18,
it was the
19.
one when upper and lower bounds of errors were defined.
Sorry. Here.
No.
I pass and you tell me when. This is just background.
Probably earlier.
Here.
No. It was noted, denoted with letter E, with dash below and over this letter E. And I think if those bounds are interval bounds, then they are incorrect. They both are positive, but not necessarily lower bound is below upper bound. Here, first line.
It's here. Okay.
In first line, are those lower and upper bounds of something? If so, they are.
I don't understand. Sorry. You mean these errors?
Yes, exactly.
Yeah.
So E is an interval.
E here is not interval. Is an error of the lower bound between the state the real state and the lower estimate or lower bound.
But it quite easily happen that E lower bound is equal to E upper bound or even exceeds it.
No, there is no relation between them. It's just the width of the errors. In the example, sorry, this not. If I try to find, yeah, for this example, for this, we have this error and this error are independent. Maybe the upper bound is lower than the other upper error. I mean, is lower than the lower error. For example, here in this we have the error is lower than the other error, lower error. So there is no relation between two errors. Just are two positive errors.
I see. So this expression in question
I will return
does not define any interval. Yeah. Those are just numbers.
Sorry?
The letter E does not mean an interval. So
no, just the width of error, upper bound error and the lower bound error.
I would say lower error and upper error, not bound.
Yeah. It's just
okay. Thank you very much.
Thank you so much.
Okay, do we have any further question in the audience? If not, I think let's thank our speaker again. I'll definitely receive the PDF slides from our speaker. I'll put it on the webpage. Then everyone can check again, yes, the error definition also on this slide, and can go through the complete design procedure. And I really very much enjoyed your presentation today. And
thank you so much.
To everyone, have a nice Friday afternoon, have a nice weekend, and let's see each other again very soon on Friday in 2 weeks.
Bye-bye, see you.